Hello, welcome to chemistry class. Today's learning objective is about nucleophilic substitution reactions. Halogen compounds generally undergo these nucleophilic substitution reactions. What are halogen compounds? Halogen compounds are obtained by replacing hydrogen atom of the hydrocarbon by halogens. You have halogen derivatives mono, di, tri, tetra, depending on the number of hydrogens. Chloromethane, methyl chloride, dichloromethane, methylene chloride, trichloromethane, chloroform, tetrachloromethane, carbon tetrachloride. And we have aliphatic halogen compounds and aromatic halogen compounds. So before entering into our learning objective nucleophilic substitutions, I have to give a brief introduction about aliphatic halogen compounds and aromatic halogen compounds. Halogen derivatives of alkanes. Halogen derivatives of the alkenes, alkynes are known as alkyl halides. Alkynyl halide, alkanyl halide, alkyl halides like that. They are again primary, secondary, tertiary. In the aromatic halogen compounds, they are obtained by replacing one or more hydrogens of aromatic hydrocarbons. So aromatic they are replaced by the halogen atoms. We have chlorobenzene, bromobenzene, chlorotoluene, so on. So let us see the chemical properties of the halogen compounds. They undergo the displacement reactions. Due to presence of partial positive charge, carbon is susceptible to attack by nucleophile, and presence of partial negative charge on halogen X facilitates it to leave halide ion. In presence of approaching nucleophile, this gives rise to displacement, that is nucleophilic substitution reactions of alkyl halides. So nucleophile plus alkyl halide gives nucleophile alkyl group by eliminating the halide ion. Now we'll see nucleophilic substitution reactions. Nucleophilic, yes, yeah. Before coming to the SN1, SN2 reactions, before coming to the SN1 and SN2 reactions, nucleophilic aliphatic substitution reactions will see. The carbon is having four bonds, one with X and the remaining is with the other alkyl group. And that CX bond of the alkyl, it is polar. It acquires carbon acquires partial positive charge. Halogen acquires partial negative charge. Presence of the positive charge of the carbon makes susceptible for the attack of the nucleophiles. Presence of positive charge on the carbon atoms makes it susceptible for attack of the nucleophile. The electron-rich species OH minus, cyanide minus, SH minus, NH2 minus, NH3 minus, NH2 minus, OR minus, R minus, R0. All these come under the nucleophiles. Nucleophile is the entering group. It enters onto the alkyl halide, thereby the nucleophile is attached and halide ion becomes the leaving group. So As the nucleophile approaches the positively charged carbon atom in alkyl halide, the halogen atom along with the bond pair of the electrons, along with the bond pairs of the electrons, the CX bonding moves away and new bond is formed between carbon and the nucleophile. So the reaction involves replacement of hydrogen by another nucleophile. The atom or the group which approaches the alkyl halide is called entering group, and one which leaves the new molecule with the bond pair of the electrons is called leaving group. And the overall reaction is called nucleophilic substitution reaction. I'm repeating, the atom or group which approaches the alkyl halide is called the entering group, and the one which leaves the molecule with the bond pair of the electrons is called leaving group. And the overall reaction is called nucleophilic substitution reaction. And the overall reaction is called nucleophilic substitution reaction. This nucleophilic substitution reaction, these are most common reactions of alkyl halides. Now, aliphatic nucleophilic substitution reactions based on kinetics and molecularity, based on the kinetics and molecularity, the aliphatic nucleophilic substitutions are divided into two types: SN1, SN2 reactions. SN1 and SN2. SN1 is unimolecular nucleophilic substitution reaction. SN2 is bimolecular nucleophilic substitution reaction. So in the SN1 reaction, substitution nucleophilic unimolecular reaction, how the reaction is, let us see. The SN1 reaction are nucleophilic substitutions. They involve nucleophile replacing a leaving group, just like SN2. So SN1 reactions are the unimolecular nucleophilic substitutions, involves nucleophile replacing a leaving group, like SN2. SN1 are unimolecular. The rate of this reaction depends only on the concentration of one reactant. So SN1 reaction happens in two steps. SN1 reaction happens in two steps. The leaving group leaves and the substrate forms the carbocation intermediate. The leaving group leaves and the substrate forms a carbocation intermediate. Nucleophile attacks the carbocation and forms the product. This is SN1 reaction. I'm going to explain you in detail by showing the diagram. SN1 reaction, in these reactions, the rate of reaction depends upon the concentration of only one species in particular substrate. In particular species. So the rate determining step involves participation of only alkyl halide. So SN1 reactions are therefore called as unimolecular because they follow first order kinetics. And SN1 reaction, in the SN1 reaction, the tertiary alkyl halides undergo this type of mechanism. It involves two steps. Consider the hydrolysis of tertiary beta-bromide with hydroxide. So first, the halide will leave and the carbocation is formed. That is the slow step, the first step. And in the second step, the nucleophile will attack the carbocation. And after that, the the nucleophile comes in attached here. Thereby, the tertiary alcohol is formed. So this is the way it proceeds. Here, SN1 reaction. This is a substrate molecule, alkyl halide. This is the substrate molecule. Slowly, first, as the nucleophile is approaching, the ligand will leave. Carbocation intermediate is formed. This is a slow step. Ligand is coming outside. It is a slow step. You can see the intermediate. And in the next stage, the nucleophile will attack the carbocation. And fastly, it will attack the nucleophile. So this attack can be from two sides. It is a fast reaction, and from two sides it will attack. Here, you can see. So you get a racemic mixture. A racemic mixture is formed. Now we'll take an example. So SN1 reaction. First one is the slow step, formation of carbocation. First step of the SN1 reaction, the leaving group leaves and the substrate carbon now has, it has 3 bonds, and the carbocation is more stable when there are more atoms to distribute. And the stability of the carbocations is more for tertiary than secondary. We'll take an example for this tertiary compound. Consider hydrolysis of tertiary butyl bromide with hydroxide ion. So first, in presence of KOH tertiary butyl bromide, the rate of reaction will follow first order. Rate of reaction will be proportional to concentration of tertiary butyl bromide. The reaction takes place in 2 steps. In the first step, bond C and bond halogen bond is broken, and it results in the formation of the carbocation. This is the slow step, hence it is the rate determining step. Carbocation so formed is the intermediate of the reaction. In the second step, nucleophile attacks the carbocation to form product tertiary butyl alcohol. So tertiary butyl bromide slowly forms tertiary butyl carbocation, and tertiary butyl carbocation, there is attack of the nucleophile, which takes place fast, and tertiary butanol is formed. The rate determining is the ionization of tertiary halide. It is affected by the polarity of the solvent. Polar solvent molecules help in ionization of alkyl halides by solvating ions thus formed. Next, the polar solvent molecules help in ionization of the alkyl halides by solvating the ions thus. Therefore, SN1 mechanism is favored in this medium. Once if you have a look onto the energy profile diagram, the energy, it has 2 transition states with carbocation as the intermediate. And at the first substrate, Rx absorbs energy E1, gets activated, high energy transition state TS1, indicated by the first phase, then rapidly decomposes into unstable intermediate carbocation by loss of some energy. The intermediate again absorbs energy delta E2 and assumes another high energy transition state TS2, as indicated by as indicated. At this stage, the second step of the reaction takes place to form stable end product, that is alcohol. So first transition step is endothermic transition state 1 and activation is delta E1. The rate determining step, it involves only alkyl halide. Therefore, it is unimolecular reactions. The second step in which nucleophile attacks the carbocation is highly exothermic. So, particular step of the reaction is fast and activation energy delta E2 is for the formation of the transition state TS2. So, the activation energy is less for this transition state. Once if you see the stereochemistry, see the first step, nucleophile attacks from two sides and a racemic mixture is formed. Yeah, the second step SN1, the nucleophile attacks carbocation intermediate, bringing the substrate loses the stereospecificity and during the carbocation intermediate. So here we can see there is a formation of a racemic mixture. SN1 reaction proceeds through the formation of carbocation as the intermediate. The carbocation is planar in shape and positively charged carbon is sp2 hybridized. The three substituents of this carbon lie in one plane with an empty p orbital perpendicular to the plane. Due to planar structure of carbocation, nucleophile can attack it from either side. So if the alkyl halide is optically active, with the presence of chiral carbon, it is expected to produce a racemic mixture which is optically inactive. So an optically active component forms the optically inactive. In these nucleophilic substitution reactions, we can in the nucleophilic substitution reactions, alkyl halide gives rise to alcohol. So two enantiomers products are not formed in equal amounts. So racemic mixture is formed due to attack of the nucleophile from two sides. The attack of nucleophile is fast, backside attack is only possible. If the nucleophile attack is slow, then the carbocation is formed. The nucleophile will attack the carbocation from either side to form the racemic mixture. If it attacks backside, it is not, you get the inverted product, which is the major product. But if the nucleophile attack is slow and the ion pair has enough time to form carbocation, so nucleophile will attack carbocation from either side front as well as from backside. Therefore, you get a racemic mixture. So, a racemic mixture. Okay. So, this is one is the inversion product and the other one is the retention. So, this is what happening in the unimolecular nucleophilic substitution reaction. Now we'll see SN2 reaction. SN2 substitution nucleophilic bimolecular reactions. Substitution nucleophilic bimolecular reactions. In SN2, the rate determining slowest step of the reaction. In the slowest step, rate determining step, substrate that is alkyl halide and nucleophiles are involved. The other way I can tell the rate of the reaction depends upon concentration of both alkyl halide and nucleophile. So SN2 reactions are bimolecular reactions following the second order kinetics. So generally it takes place in primary alkyl halides. Primary alkyl halide will form primary alcohol the substitution of the alkyl halide is done by the OH group. So a weaker nucleophile is replaced by a stronger nucleophile. Weaker nucleophile is replaced by a stronger nucleophile. Next, we'll see is observed during the alkaline hydrolysis of methyl bromide with aqueous sodium hydroxide. Will take methyl bromide, sodium hydroxide, we get methanol plus sodium bromide. During alkaline hydrolysis of methyl bromide with alkaline sodium hydroxide or moist silver oxide, the reaction follows second order kinetics. The rate of the reaction is proportional to the concentration of both methyl bromide and sodium hydroxide. The rate of the reaction, it is proportional to concentration of alkyl halide as well as the concentration of the nucleophile. Reaction takes place in single step, proceeds through the formation of intermediate transition state. So the reaction will be initiated by the entering OH group, approaches the carbon atom from opposite side of bromine leaving group and forms partial bond with the carbon atom simultaneously. The substitution involves substitution. Two reactants produce two products. Things have been switched around. Substitution. Here. This is the alkyl halide, primary alkyl halide. Nucleophile is coming towards the carbon atom, and thereby the nucleophile is stronger and this nucleophile is weaker. So the bond is weakening for this ligand, the leaving group. There is simultaneous bond formation of the nucleophile and there is simultaneous cleavage of the ligand. Therefore, a weak bonds are formed between these two. So carbon, you can see nucleophile and the ligand, both of them weaker bonds are formed. And here is a transition state. There you can see carbocation formation. That is a two-step mechanism. SN1 is two-step mechanism. Carbocation formation, nucleophile attack. This is single-step mechanism. There you can see intermediate. And here you can see only transition state. There it takes place in tertiary alkyl halides. Here it takes place in primary alkyl halides. And further, this nucleophilic, this transition state, if you see here, this transition state, there is simultaneous bond cleavage and bond formation. And later, the bond is broken and the bond is formed. So, if the first one is the rate determining step, where there is rate is dependent on the nucleophile concentration and concentration of alkyl halide. So you call it as bimolecular reaction. Rate is dependent on two concentrations. Into summary. So nucleophile backside attacks the positive carbon center. Transition state forms where the nucleophile is formed. The leaving group leaves, forming the final product. In SN2 reaction, the nucleophile, these reactions involve nucleophile replacing the leaving group. Nucleophile attacks the substrate, donating an electron pair to the new bond and replaces the leaving group, that is the substitution. So nucleophile, nucleus-Slavic groups are the nucleophiles. Now, how the stereochemistry, once if we have a look onto that, how it takes place is, or else we can even observe the stereochemistry. So I'll explain you in detail. We'll take Example for methyl bromide on reaction with sodium hydroxide, you get methanol and sodium bromide. The alkaline hydrolysis of methyl bromide with aqueous sodium hydroxide or moist silver oxide. The reaction follows second order kinetics. Because the rate of reaction is proportional to concentration of both methyl bromide and sodium hydroxide. So rate is proportional to methyl bromide and hydroxyl concentration. It proceeds through the formation of the intermediate transition state. The reaction is initiated by OH entering group and approaches the carbon atom from the opposite side of bromine. It forms a partial bond with the carbon simultaneously, and the bond between the carbon and bromine becomes partial. The negative charge on the hydroxide diminishes by the intermediate state of the reaction center is surrounded by 5 groups. As previously, it is here. Attached by the 5 groups, having partial bonds with entering and the leaving groups, and the negative charge. See, negative charge spread through one end of the molecule to the other end is called transition state of the reaction. In transition state, the reaction center of the substrate is sp2 hybridized. The thin hydrogen atoms attached to it lie in the plane with bond angle equal to 120 degrees. So the CH bonds are thus arranged like spokes of wheel, while COH, C bond, Br bonds are along the bond axis. The energy profile diagram shows the presence of single transition state at highest energy state and no intermediate is found. The reaction is exothermic reaction. Transition state is highly unstable due to presence of high energy and pi bonds around the carbon atom. In the energy profile diagram and the stereochemistry, finally, if we see in SN2 mechanism, due to the rare attack of the entering group, proceeds with the inversion configuration. Inversion configuration, so it's called as Walden inversion. C bond Br is fully cleaved and energy required to it is partially provided by the C bond OH. The OH group attacks the position just opposite to that of bromine. Just opposite to that of bromine atom. The SN2 mechanism, due to the rare attack of the entering group, proceeds inversion of the configuration called as the Walden inversion. In SN2, the nucleophile attacks the substrate from the back and results in the inversion of configuration. Here it can be demonstrated by taking alkyl halide having chiral carbon. Consider the alkaline hydrolysis of, you can consider even 2-bromo-octane. You can even consider the hydrolysis of 2-bromo-butane. So you can see for this primary alkyl halides, inversion of configuration is accompanied. It is accompanied by the change in the direction of rotation. Two compounds are in the same direction. See, here you can see the inversion of configuration. It is caused due to the change in the direction of the rotation. So once if you see the differences, SN1 and SN2, how it's taking place. And for this nucleophile SN1, SN2, I'm going to give you a detailed differences. Before that, what are the factors that are affecting the SN1, SN2 reactions? Structure of the alkyl halide, nature and concentration of the nucleophile, nature of the leaving group, polarity of the solvent can affect the nucleophilic substitution reactions. SN2 reactions, replacing group, nucleophile attacks the substrate, donating the electron pair to the new bond and replaces the leaving group. That is the substitution. See, SN2, how it's taking place. This is the leaving group and the nucleophile. This is the substrate. Thereby, nucleophile is attacked from the backside, getting the inversion of the configuration. So, SN2 reaction, it is a bimolecular reaction whose rate depends on the concentration of two reactants, SN2. Takes place in one step. Nucleophile attacks the substrate at the leaving group, leaves the substrate. See, and SN2 reaction, the nucleophile attacks from opposite region, the backside attack causes inversion. The nucleophile must be able to reach the positive carbon center, and thereby the Walden inversion will take place. See, I'm going to explain you the differences between the SN1 and SN2 reactions. Coming to the SN1 and SN2 reactions, I'm going to explain you the differences. As we have seen SN1 and SN2 reactions, the differences are in SN1 reaction and SN2 reaction. SN1 is the bimolecular reaction. SN2 is the bimolecular reaction. SN1 is the unimolecular reaction. In SN2 reaction, nucleophile attacks from backside. In SN1, nucleophile will attack from back as well as from the front side. Walden inversion is observed in SN2. Partial racemization is seen typically active alkyl halides. You can observe steric hindrance influences. Steric hindrance will influence the rate of the reaction for SN2. Electronic factors influence the rate of reaction largely. High concentration of nucleophile favors the reaction. Low concentration of the nucleophile favors the reaction for SN1. So for SN2, high concentration of nucleophile favors the SN2 reaction. For SN1, low concentration of the nucleophile favors the reaction. And for strong nucleophiles like alkoxide ion favors the SN2 reaction. Mild nucleophiles like water ammonia favors the SN1 reaction. And SN2 reaction, you can see racemic, you cannot see racemic mixture, but Walden inversion is observed. In SN1 reaction, no Walden inversion is observed, but partial racemization is seen. In SN2 reaction, there is backside attack. For SN1, there is both front and backside attack. SN2 reaction takes place in single step. SN1 reaction takes place in two steps. In SN2 reaction, we can see transition state, no carbocation. In SN1 reaction, we can see carbocation but no transition state. SN2 takes place in primary alkyl halides. SN1 takes place in tertiary alkyl halides. Rate of the reaction increases with the polarity of the solvent in SN1. Rate of the reaction decreases with the polarity of the solvent. The order of reactivity of the alkyl halides is in SN1, benzene, allynes, tertiary, secondary, primary, then methyl halides. Order of reactivity is methyl, primary, secondary, tertiary halides for SN2 reactions. So you can see Walden inversion SN2. SN1 we can see the racemic mixture formation. So these are the differences between the SN1 SN2 reactions. I have explained you clearly about the nucleophilic substitution. Generally takes place in the halogen compounds. And these halogen compounds SN1 SN2 reactions. The differences, the rate of the reaction, the stereochemistry, energy profile diagram. Everything is discussed in this session. I hope you have understood today's class. So SN1 reactions and SN2 reactions. How they are taking place we have seen. Thank you all for listening to my class. And this is the end of the class. Thank you everybody.